At the time this program was recorded, a Category 5 storm, Hurricane Melissa, was raging in the Caribbean, set to move into Jamaica with the risk of catastrophic damage. The storm had 175-mile-an-hour winds. Officially, movement was northeast at 2 knots, but we still see some wobble on the satellite imagery. To predict the track in a true scientific manner, we all turn to forecast models because there's simply no way for humans to beat the models with manual techniques. We tried that up into the 1960s with limited success. We have much better tools available now compared to then, or even compared to 30 years ago. So the big question is, what are all these models? Which ones do we need to be looking at? I'll try to help simplify things a bit, though the underlying topics will still be a bit complex. On sites like Pivotal Weather and Tropical Tidbits, we can view a large variety of global and regional weather models. These are definitely useful for giving you the track from the deterministic global models, and they do have the ensembles on there as well. Pretty wide variety of different products. But when a hurricane is underway, you want to go to these specialized sites like tropicalatlantic.com, which have a large number of more specialized hurricane tracks in a common format. They're not generated by Tropical Atlantic, but they come from the National Hurricane Center's data server. There's probably other sources to get these tracks, maybe some apps on your phone. But this is one of the easiest. Simply go to the website tropicalatlantic.com, click on the storm name at the top, and scroll down to this model map, and that'll take you right where you need to go. By clicking on these different codes over on the right, you can bring up the different paths from each model. You can even view all of them. Now that gives you the so-called spaghetti plot that you see on social media. But displaying all of them like this is a bad idea because you don't know which ones are contributing useful data and which ones aren't. Not all of these are useful. And besides, how can you find the best performing member in there? So as we go through this, we're going to go through them individually and learn which ones are better and which ones you should avoid. As we go through this, you're going to notice on the right-hand side, this is split up into early models, and a little ways down we have the late cycle models. Early guidance refers to model forecasts that use the previous model cycle, adjusted using the latest hurricane track to match the latest advisory time. Late guidance refers to model forecasts from the most recent full model runs. Those arrive late because they must wait for the newest data to be assimilated and for the model to complete its run. First up is the OFCL product, the official forecast issued by the National Hurricane Center. That represents the authoritative track, intensity, and wind forecast for a tropical cyclone. And that is what makes it unique. It's a human-machine blend. You're looking at dynamical models, statistical models, consensus aids, ensemble spreads, all of that going into the forecast, satellite imagery, aircraft recon data, and that synthesis is what makes OFCL so valuable. It also serves as the reference track for downstream products like storm surge forecasts, wind probability maps, and rainfall guidance. There's also OFCI. This is the 6-hour adjusted and interpolated track. This helps forecasters evaluate consistency and track the evolution of forecast changes. It takes the previous cycle's OFCL and adjusts its starting point to line up with the storm's current observed position from the newest advisory. For this presentation, we'll leave the OFCL as a reference line to show the forecast of Hurricane Melissa related to the current models on the evening of November 27th, 2025. Next up is NOAA's GEFS, the Global Ensemble Forecast System. That's the ensemble counterpart to the deterministic GFS. It's indicated by the codes AEM, AC, and AP, with AP going from 01 to 30. It uses 30 lower resolution GFS runs. Here's where it gets interesting. Each of those runs has a different perturbation. essentially a small variation which is introduced into the model. This helps create variability in the forecast solutions, which is crucial for understanding the range of possible outcomes. We start out with AEMN. That is going to be the ensemble mean. That's the average of all the ensemble members combined. The ensemble members themselves are AP01 through AP30. So you can examine each one separately if you want to. That shows you some of the outliers, but these are fairly well clustered, all of the ensemble members tracking into eastern Cuba. Then there's AEMI, which is the 6-hour interpolated version. This I on the end is seen on various products, and that tells you that it is a 6-hour interpolated version. Those correct the previous model run based on the latest observed storm track. When it's available, it gives forecasters a more up-to-date picture. Then we have AC00. That is the control run of the ensemble forecasting system. That run has no perturbation applied, which makes it valuable as a baseline or benchmark for evaluating how the entire model system is performing. Now let's move on to the AVN product, which is known as GEFS, the Global Forecasting System. You might be wondering, why is it on here as AVN? That's actually a legacy code dating back to the 1970s and 1980s, when this model's predecessor was known as the Aviation Run. Then through the 1980s and 1990s, it evolved into the MRF, the Medium Range Forecasting System, but the naming convention for AVN stuck. Today we have the AVNO, which is the regular model run, and the AVNI, which is the 6-hour interpolated version that corrects for the latest observed storm motion, similar to what we saw with the GEFS. The GFS runs 4 times a day and forecasts atmospheric conditions out to 16 days. Under the hood, it uses the FV3 dynamical core, which solves the full fluid dynamics and thermodynamic equations that govern our atmosphere. Here's an important distinction. The GFS excels at providing the large-scale environment and steering flow that are critical for tropical cyclone track forecasting. It doesn't use a specialized inner core hurricane physics package. Because of this, the intensity forecasts are not all that accurate, but the GFS is one of the foundational guidance systems that forecasters rely on when assessing storm tracks. It's pretty dependable out to a week, making it an essential tool in the tropical forecasting toolkit. Next up is the CEM product. That's Canada's ensemble forecast system. This includes CEMN, which is the main run, along with CEMI, which is the interpolated version, and CEM2, the 2 on the end. See if we have that here. Yeah, that right there, that 2, when you see a 2 on the end, that tells you it's a 12-hour interpolated version. So it's using an older version of the model and updating it with current conditions. The data behind the CEM comes from the Canadian Meteorological Center's Global Environmental Multiscale Model, known as the GEM Ensemble Prediction System. It's a comprehensive global dynamical modeling framework that assimilates observations, atmospheric flow, storm motion, intensity data, but it's not a specialized hurricane forecasting model. Its track record is not as good as the GEFS and the European Ensemble, but still it provides valuable independent guidance, in having multiple global model perspectives helps forecasters build confidence when different systems agree. The CMC product is Canada's deterministic global weather model, known as GEM, the Global Environmental Multiscale Model. It is the deterministic single-run high-resolution counterpart to the Canadian GEM Ensemble. Like other global models, it solves the full atmospheric equations across the entire globe, incorporating modern data assimilation and a detailed physics suite. You'll also see CMCI and CMC2, which are the 6-hour and 12-hour interpolated versions of the same model, which provides early forecast positions. Now, the CMC sometimes shows more spread and variability in tropical cyclone tracks compared to heavyweights, like the European and GFS. But that variability can be valuable. It reminds forecasters to consider a wider range of scenarios. It remains an important consensus contributor. When it aligns with the other major global models, that agreement signifies confidence in the forecast track. Next up is the CLIP-5. Wow, that goes way off to the northwest. That's the NOAA Climatology and Persistence Model, and it's purely statistical. It's used by NHC. Now, this one is different from everything we've discussed so far. It serves as a baseline or control against which more sophisticated models are judged. CLIP-5 does not use real-time atmospheric physics or numerical simulation at all. Instead, it projects the storm's future motion by combining a couple pieces of information. One is persistence, and the other is climatology, looking at historical tracks of past storms that occurred in a similar location. The key limitation is CLIP-5 doesn't respond to changing weather patterns. It can't account for an approaching trough or a building ridge. Because of that, its skill is intentionally limited, and it should not be relied on for any actual hurricane forecasting. CTC is the product code for the COAMPS-TC model, with CTCX being the main run and CTCI being the 6-hour interpolated version. COAMPS is a coupled atmospheric mesoscale prediction system, and it's the U.S. Navy's specialized regional model. What sets it apart is the resolution and coupling qualities. It uses nested high-resolution grids that zoom down into the storm's inner core down to about 3 to 9 kilometers, much finer than what global models can achieve. More importantly, it's coupled to an ocean model, which means it can represent critical processes like eye-wall structure, heat fluxes between the ocean and atmosphere, ocean mixing effects that directly influence a storm's intensity. Because of its high resolution and ocean coupling, COAMPS can sometimes capture storm structure and intensity changes better than global models, particularly rapid intensification or weakening events tied to ocean interaction. However, its track performance varies by region, and it's notably sensitive to the quality of the initial vortex representation and the availability of observational data going into the model. When those work out well, it's a very powerful tool. When data is sparse, its performance can be more variable. Then we have EAI, which is the European ECMWF AIFS, the Artificial Intelligence Forecasting System. This replaces or complements many of the usual physics-based equations with a deep learning pipeline. It uses the same kind of high-quality initial fields used by the traditional models, and then uses a graph neural network encoder-decoder and a sliding window transformer to learn how the atmosphere evolves. That's built on a database of decades of reanalysis and past forecasts. Because it leverages machine learning rather than solving the full set of physical equations, AIFS is far faster and far more energy efficient than traditional models and seems to show improved skill in certain areas. As it's a rather new model, its skill is uncertain, but it has had some pretty good successes, one with Hurricane Milton, and it seemed to handle the path of Melissa pretty good about 2 to 3 days out. The European ECMWF EPS, or Ensemble Prediction System, is the European counterpart of the American GEFS. It's a probabilistic global forecasting framework that runs 50 parallel model simulations, all of them based on the same high-quality global model known as the IFS. This gives a probabilistic spread of possible storm paths and intensities. The product ECME is the control member, which is run without any perturbations and is a benchmark path. And the EE fields, those are the individual ensemble members with perturbations. Those run from 0, 1 to 50, and they can be viewed individually to show the spread of possible scenarios. The ECMO product is the European ECMWF deterministic model known as IFS HRES. That's the European counterpart of the American GEFS deterministic model. Like all deterministic dynamical models, it integrates observations from satellites, aircraft, ships, radiosondes, surface stations into a 7-day and later forecast at a resolution of 9 kilometers. The ECMO is often the most trusted single-member model for track forecasting, but it is not a storm-scale model, so it doesn't forecast intensity as accurately as the more specialized models. Next, we get into the Google DeepMind models. Now, admittedly, I don't know much about the skill of these particular models as I haven't done a comparative study on them, but I welcome any comments about what you've observed. In 2023 and 24, there was the WeatherNext graph and gen models, followed in 2025 by the advanced probabilistic ensemble AI system called FNV3 that builds on the same architecture that created its earlier systems. This uses gridded fields of temperature, humidity, and pressure. It does not solve the traditional dynamical fluid equations, but applies a learned atmospheric transition function forward in time. It's trained on decades of global reanalysis plus a tropical cyclone-specific database, and can generate up to 50 scenario realizations out to 15 days. It's still considered experimental, but it is a major step towards integrating deep learning-based hurricane forecasting into operational workflows. We are going to skip HCCA and come back to that later because that's very important. We're going to get into the HFA and the HFB. That also comes in under HFS. Those are the Hurricane Analysis and Forecast System, or HAFS. HAFS was developed by NOAA and uses the FV Dynamical Core. It comes in 2 versions, the global HAFS-A and the HAFS-B for NHC basins in the Atlantic and Pacific. Both systems feature storm-following nested grids, advanced vortex initialization, ocean wave processes, and so on. The main difference is HAFS-A is a more generalized model suitable for global implementation. HAFS-B uses a specialized microphysics scheme for very intense storms, and it's designed for the Atlantic and Pacific basins. Because of that, HAFS-B is often preferred at NHC. HMON is an older NOAA model from 2017 that replaced the GFDL model. It was designed to provide higher resolution guidance on the structure, intensity, and inner core evolution of tropical cyclones. It was built on the inset fork of the WRF model. It uses a storm-centered moving nest, typically down to about 3 kilometers resolution. It was replaced by the HAFS model in 2023. HW is the code for the HWRF, an older, higher-resolution regional hurricane forecasting system developed by NOAA and partners, which uses the WRF dynamical framework with a storm-centered moving nest and coupling to ocean models. However, this is an older model. While it brought major advances such as reduced track errors and better representation of storm structure, it does have limitations, such as computational cost and a tendency for performance to degrade when storms interact with land or complex sea currents. It was replaced by the HAFS model. NGX refers to the NAVGEM, the Navy Global Environmental Model, which is the U.S. Navy's global dynamical weather model that solves the full atmospheric equations and provides forecasts out to medium range. It replaced NOGAPS in 2013. Its skill is not strong compared to the European GFS and consensus models. In my own verification studies, I've found mediocre performance with landfalls in the U.S., but it's often checked alongside those models to identify agreement or disagreement in storm path scenarios. It can be useful for detecting track shifts tied to developing troughs, ridges, and so on, but again, it is less reliable than the mainstream models. Then we come to the TAB models, the trajectory and beta model. These are simple trajectory-based track models that move a tropical cyclone forward based on observed steering flow, rather than solving full atmospheric equations. We have the TABs, which is the shallow layer from 850 to 700. That's typically used for new developing tropical cyclones. We have the TABM, which is the medium layer. That's from 850 to 400 millibars, in other words, about 5,000, up to 23,000. That's good for larger storms. And TABD, which is from 850 to 200. That's the deep layer. And that goes all the way up to about 40,000 feet. That's used for the largest storms, but I found that the TABM sometimes accurately captures the 48-hour movement, because basically the tropical cyclone is embedded in the prevailing winds. So those models are actually interesting, if not useful, for highlighting how the storm might move if it follows the prevailing environmental flow. It provides a quick way to identify which layers of the atmosphere are currently steering the storm. So when there's unexpected movement, you can consult those products and see if the prevailing flow has changed significantly. Next up is the T-clip, the trajectory clipper, and that goes way off to the northwest. That is a climatology and persistence model. It does not use real-time atmospheric model output. As you can see there, instead it combines the storm's recent motion with the average historical tracks of past storms that were in similar locations. It does not respond to changing steering patterns, trough interactions, ridge strength, or anything like that. It's intentionally simple, and it's mainly used as a reference or control forecast. It shows what the storm would do if nothing in the environment meaningfully changed. Then we have our final dynamical model, the UKX, which is the UK Met Office Global Model, often just called the UK Met. This is a full global dynamical model that solves the atmospheric governing equations with a sophisticated data assimilation system and physics suite. UKX often performs well with a large-scale steering flow, so it's generally stronger on track forecasting than on intensity, but it can still struggle with rapid structural changes in the inner core. UKX is the normal output, UKXI, the 6-hour interpolated version, and the UKX2, the 12-hour interpolated version, for comparison or contingency use. And then there is XTRP, the extrapolated track, which is way out there compared to the official forecast. This is a very simple short-term guidance tool that projects the storm's motion based solely on its recent observed movement. It doesn't take into account any atmospheric model data. This is not recommended for use for forecasting. It's only a short-term situational check. Then we get into the consensus models, and these I really like. HCCA, that's used heavily by the National Hurricane Center. That's the Hurricane Center Consensus Aid. It's a weighted consensus forecast model that combines several of the highest performing dynamical track and intensity models, such as the GEFS, the European, UK Met, COAMPS-TC, along with recent official forecast performance statistics. It applies adaptive weights based on how well each model is doing. So models that perform very well will bias the results a little more heavily, which makes it a very valuable tool. This is a very useful tool for when the major models are disagreeing, because the consensus tends to reduce the individual model biases and produces more stable track forecasts. The TVC products are all consensus track models. They're similar to the HCCA, but they use simpler weights. Unlike HCCA, which is designed as a real-time tool for NHC forecasters, the TVC products are more of a general forecasting tool. TVCN was developed as the base consensus model for use in all basins. TVCA is intended for the North Atlantic and TVCE for the Eastern North Pacific. TVCX is a weighted experimental consensus variant where certain members are given extra weight. TVCC is a bias-corrected consensus model. As with HCCA, the recipe for the TVC consensus models are changed from season to season, so we can't say specifically which ones are the best right now. Sometimes forecast discussions will talk about that. In tropical forecasting, all of these consensus aids are often outstanding track predictors, especially beyond 48 hours. When the consensus guidance clusters tightly, track confidence is high. So we've returned to the official NHC track. We're going to get into the wind and intensity models. These have no native track forecasting. They draw upon the official NHC track. So there's no purpose to look at them for track information unless you specifically want to click on the track waypoints to see the wind or intensity. Some of those products are going to be DRCL, the De Maria Climatology and Persistence Model Intensity Forecast. And you can see you can click on those points to see what it's forecasting. There is DSHIP, the Statistical Hurricane Intensity Prediction Scheme. There is NAVGEM, the Logistic Growth Equation Model that forecasts intensity. There's NNIB and NNIC, which are the neural network intensity models, the baseline and the consensus. There is OCD5, the Operational CLIP5, and DSHIFOR, Blended Intensity Forecast. That gets its track location from the CLP5, so if you clicked on that, there's no reason to click on the OCD5 unless you want to look at the data points. RVCN is the Wind Radii Consensus, again, that uses official NHC information. And SHIP, the Statistical Hurricane Intensity Prediction Scheme, again, that follows the official NHC track. So there's no point on clicking on those or these unless you want to actually look at the data points. And that's pretty much it. So let's see how we're doing with verification. We're about 9 hours into that forecast cycle. The storm was stationary about 9 hours ago, and now it's drifting to the north-northeast. It's pretty tough to extrapolate that because we've got some wobbling going on, but it looks like it is heading towards the western part of Jamaica. And here is the Kingston radar from 0Z, the beginning of that cycle, 8 p.m. Eastern, all the way up to 0828 Zulu, which is, that's going to be 4:30 a.m. So this is 9 hours, 8.5 hours into the cycle, and you can see the eye of the storm moving northeast. And there is the close-up scan showing the eye starting to come within range of that closer view. And yeah, I think Jamaica is going to be dealing with some problems, unfortunately, today. The good thing is it's going to come through during the day, so that will reduce the risk a little bit. Nighttime hurricanes, they're not only terrifying psychologically, but they're also dangerous because of the limited amount of light and the significantly increased hazards, not only outside but also inside. And there is the Dvorak imagery. This is certainly a very unusual annular eye, very, very cold, and that medium gray ring going all the way around the storm. So this is certainly consistent with a Category 5 storm. So it is going to be a tragic day, unfortunately, in Jamaica. I'm really sad to see this. Most of the island will be hit pretty hard, especially the west. they're going to bear the brunt of this, and especially on the right side of the track. So it's probably about several hours away from making landfall right now. 175 miles an hour, that's exactly the same as when Camille came onshore in the U.S. back in 1969. So hopefully there's some lessons in there to be learned for this and any future storms. Feel free to write in comments if you have any corrections, anything that varies from what I said. And this afternoon, we're going to have another episode of Forecast Lab. We're going to go into more detail on the storm, and we typically do that show twice a week, so hopefully we'll catch you there, right here on this channel. All right, take care, and we'll see you soon. Bye-bye.